In this video, we'll take a deep dive into the transformer architecture. By the end of this video, you'll have a clear understanding of how AI-powered text models are built. Step 1. Input processing. Let's break it down with an example. The cat sat on the mat. First, we tokenize, splitting the sentence into words or subwords. Each token is then converted into a numerical vector known as an embedding, which represents the word's meaning in high-dimensional space. For example, cat might turn into a vector like 0.25, 9 is 0.47.63. But there's a problem. Transformers don't understand word order. To fix this, we add positional encoding, which helps the model recognize the sequence using sine and cosine functions. Step 2. Encoder processing. Now let's enter the encoder block, where the real magic happens. Each encoder layer has two key components: multi-head self-attention and a feed-forward network. Multi-head self-attention. Here's where the model decides which words to focus on. Each token generates three vectors: query Q, key K, and value sta. These vectors determine attention scores. For example, when processing cat, the model calculates dot products between cat's query and the keys of other tokens. This tells us how much importance cat should give to sat or mat. And since different heads focus on different aspects like syntax, meaning, or context, multi-head attention captures multiple relationships in parallel. Feed-forward network. Once self-attention is done, the output goes through a feed-forward network, FFN, two linear layers with a ReLU activation in between. This adds nonlinearity, making the model more powerful. A residual connection preserves important information, and layer normalization stabilizes training. Step 3. Decoder processing. The decoder works similarly to the encoder, but introduces one big difference: masked multi-head attention. This ensures the model only sees past tokens, preventing it from cheating by looking ahead. That's the model blocking future words from influencing predictions. After that, the decoder performs multi-head attention over the encoder's output. This helps it align with important input words before passing through a feed-forward network for further processing. Step 4. Output generation. Now comes the final step. The decoder's output passes through a linear transformation and a softmax function, converting raw scores into probabilities. The model picks the most likely word at each step, iterating until the sentence is complete. Real-world impact. Modern transformers scale to billions, even trillions of parameters. First, they undergo pre-training on massive datasets, then fine-tuning for tasks like translation, summarization, or coding. Some models even use reinforcement learning to align with human preferences. And that's the power of transformers, completely revolutionizing AI. If this breakdown helped you, don't forget to like, subscribe, and drop a comment below.